Yeah, hi and welcome. Nice to see so many people here. I'm really excited to speak here. We will present a session, a practical session on learning about heterogeneous graphs with PyGeometric or PyG. And I myself am Matthias. I'm from Dortmund, Germany, and we'll be speaking here with Ramona, which is my colleague at Kumo AI. And I will go through GNNs and why you should be interested in them and why are they the best choice for machine learning on graphs. And then I will also introduce PyG, like best practices, challenges, and so on. And then we'll hand off over to Ramona, which will go through the practical session, which you can also follow on your own devices. And so, just as a quick introduction, why we should care about GNNs in particular. And so if we look at the modern deep learning toolbox, then we see that this toolbox is heavily designed for simple sequences and grids. And so we traditionally use like convolutional neural networks to process images or transformers, and we also use recurrent neural networks and so on to process sequences. But not every problem can be framed as such, because like not every input we can think of can be represented as a grid or a simple sequence. And so the main motivation here, or the main question we ask is, how can we develop neural networks that are much more broadly applicable? And so if we look at the real world, then we see that nearly everything can be represented as a graph. And a graph usually consists of a set of nodes that are our entities in our world. And then the edges between these nodes denote how these two entities relate to each other. And so, for example, a social network is a prominent example of a graph where we have users as entities, and then we have edges connecting these users and so on. Other examples are, for example, traffic networks, communication networks, and so on. And we can also see that on all different kinds of scale, we can use graphs. So we can really use graphs for describing high-level concepts such as social networks, but we can also think about describing molecules as a graph and use neural networks to process them. And so the main problem we have here is that graph data is different from grids and text. And so in particular, they can have like arbitrary sizes, which means like the number of nodes, for example, may be different. There's some complex topological structure beneath them. Secondly, we usually have no fixed node ordering or reference point. So if you think about like a CNN, then it is clear that if we apply a CNN, then we can directly reference like the top right pixel to the current pixel, but there's no such definition in a graph. And so we usually speak about no fixed node ordering here. And then graphs are often dynamic, which is in contrast again to images or text, because I've rarely seen a graph that is not changing over time. And lastly, we are speaking about, in practical cases, we are mostly interested in heterogeneous graphs. And that means that we have different types of nodes and different types of edges. And to these different node types, we have different node and edge features attached to them, which makes them kind of a multimodal problem to tackle. So if we look at the traditional machine learning pipeline on graphs, we are questioning ourselves, like how can we capture this network structure as input feature? Or how can we combine this network structure that we processed and combine them with attributes such as nodes and edge features? And especially, how can we use that to perform tasks at different levels of the graph, such as the task at the level of nodes, edges, or graphs? And then we see that if we put that into machine learning pipeline, then we actually use many different tools and frameworks to process them. So for example, we use pandas or NumPy for feature engineering. We do some data splitting and so on with sklearn. And then we process that all into like a tabular data layout, and then use XGBoost or neural networks, MLPs on top of them to apply them. And so there are two prominent approaches in doing that this way. And the one I mentioned earlier is known as some kind of preprocessing node features. And the goal here is that we kind of capture network structure as input features. And so one way to specify like how important the node is in a graph may be the node degree, which simply describes the number of neighbors attached to that node. We can think about more complex input features such as node centrality measures, clustering coefficients, and so on. But the ultimate drawback here is that all these features are super arbitrary. So we do not really know in advance what features we are really interested in our network structure. It is also expensive to compute, especially some kind of clustering coefficients and so on. And ultimately, we are losing signal because we just, the final machine learning model has just input to the features we pre-processed in advance, but not has no access to the raw graph. The second traditional machine learning model, which was kind of popular like 3 or 4 years ago, is known as the shallow embedding model, and that references the lines of work of deep walk or node-to-vec, and those are all like random walk based, which means they're built on the intuition that we embed each node in an embedding space based on whenever two nodes are nearby in the graph, we want their embeddings to be nearby in the embedding space. And if we have two nodes that are like far away in the graph, we want also their embeddings far away in the embedding space. And so we usually train that in like a word-to-vec or contrastive learning scenario where we sample random walks and then push all the embeddings of this random walk, of the nodes inside this random walk together, and then sample negatives and we push them away. And ultimately, that works well for some kind of link prediction task, but it has drawbacks as well. In particular, it is super hard to scale because we basically learn a shallow embedding matrix for all nodes in our graphs. And if we think of really big graphs, that is like a giant embedding matrix we need to learn here. We are using like an unsupervised learning loss, which does not necessarily align with the task we are interested in. And it is transactive by nature. That means whenever a new node comes in, or we want to apply that model on a different graph, then we're basically stuck. And so graph neural networks got really prominent in that sense because it does not have all these limitations. And in the essence, graph neural networks are best described as some form of neural message passing scheme, in the sense that nodes send messages to their neighbors, they got aggregated, and these messages get learned and trained. And so I personally see them as some kind of generalization of any neural network architecture, and I find this kind of cool, because what we have here is basically that we're using this input graph and use that as our computation graph inside our neural networks. And so that's actually a new paradigm of how we define neural networks, in the sense that we no longer have static computation graphs in our neural networks, but we actually input the computation graph into the neural network. And so that naturally allows us to use graph neural networks as a super high-level concept to go, for example, from CNNs to GNNs, in the sense that we are moving away from discrete neighborhood sizes and allow like dynamic neighbors arbitrarily positioned in space. And we can also see them as some form of generalization of transformers, which is, in the concept of GNNs, just a neural network that operates on a fully connected graph in which every node is connected to every other. And then we're using attention to pass messages between these nodes. And so how does that work in a formular way? And so graph neural networks can be described as a way to update node representations by repeatedly transforming and aggregating informations of direct neighbors. So we're having this function here called f, and that is parameterized, so it can be learned. And it takes in the input features of the node we are interested in, and all the input features of this direct neighbor. And then it uses this information to compute a new feature vector or a new embedding for this node we are interested in. And so that scheme below here shows it quite nicely. We have the central node here, which is marked as a green node. The blue nodes send their messages to this green node. They get aggregated, and that information is then used to compute a new representation for the next layer. And so they have some ultimate graph neural networks has some nice property and strengths. For example, all these GNN layers can be trained because all of them are differentiable. And so you could think of them as having some kind of sub-neural networks that describe how we aggregate information in each different layer. And so if we're looking at the graph here on the left, and we want to compute a representation for this target node, then this will amount to the computation graph shown on the right, where all these little gray boxes denote how we aggregate information at all different stages. Importantly, each node uses the same set of parameters, or these parameters are shared, which makes GNNs inductive by nature. So we have no problems using them and apply them on new nodes or graphs. And then GNN layers, as in CNNs and other architectures, can be naturally stacked, and that helps us to reach long-range information from nodes far away from the target node. GNNs, in the essence, just are responsible for giving us a node representation, but we can use this representation then for a given downstream task. And the most popular tasks are known as node classification, graph classification, and link prediction. So in the node classification, we want to predict the class of a given node. So we have a neural network that gets the graph as input, and a specific node V we are interested in making a prediction for. And so we can directly use the layer, the representation produced by the GNN, which is here H in the else layer, and use that representation and input that into an MLP to make the final prediction. And that is all trained end-to-end. Similar in the graph classification case, we are using GNNs to compute a node representation for all the nodes in the graph. We aggregate them together in a permutation invariant way, and then apply a MLP on top to get a prediction for a single graph. Sorry. And in the link prediction case, we are now want to make a prediction for a source node and a destination node. So the neural network gets as input the graph, and then the link we want to make a prediction for, in that case, V and W. And for example, we can then use an MLP as well, which is concatenate the embeddings of the GNN to make a prediction for a given link we are interested in. Importantly, and that is probably why we're here, implementing GNNs is ultimately challenging, especially because it does not really follow the traditional deep learning toolbox we all know. One of these challenges is sparsity and irregularity, which means that all our graphs we want to process are ultimately dynamic and may change in size and neighborhood sizes and so on. And there arise questions such as, like, how can we effectively parallelize this data and so on. There's an underlying constraint of heterogeneity in the underlying data. So we have input features that can be numerical, categorical, they can be even images and text. And that may also be different across different node types and edge types in our graph. And then, as mentioned earlier, graphs are usually dynamic, and it's hard to find scenarios in which graphs will not change over time, so you need to take that into account. And then there exist various different requests on scalability, in the sense that some graphs may be more sparse than other graphs. Sometimes we even work on highly dense graphs or fully connected graphs and so on. And then there is this tradition, or this classic contrast between operating on many, many small graphs, which might happen if you think about like a molecule data set, where each molecule has like 10 or 20 nodes, but we're actually working on a data set that contains like millions of molecules, versus operating on a social network where we just have a single giant graph, but that single giant graph may consist of millions of billions of users. And then there's the applicability to a set of diverse tasks, in the sense that our framework, or how we implement GNNs, should not restrict to which task we want to apply that GNN. So we have node level, link level, graph level tasks, as mentioned earlier, but that also should naturally support tasks such as clustering, pre-training, self-supervision, and so on. And so our solution to that, which is fully open sourced, is called PyG, or previously known as PyTorch Geometric. And the goal here is that we have a PyTorch-based framework that bundles the state-of-the-art in graph representation learning by implementing various layers, architectures, and examples known from latest research. And so I'm especially proud of over 350 contributors now. And in particular, that whole project has kind of grown from like a single person project to a project that is now maintained by many, many people and many, many different companies, such as different universities, our own startup, Kumo AI, as well as NVIDIA and Intel. And so in the essence, PyG contains 4 major components. One is that it contains graph-based neural network building blocks. So it contains message passing layers, so GNN layers known from latest research, graph-based normalization layers, pooling layers, readout layers, and so on. And they are all defined on unified interfaces such that it can easily be extended, and you can easily implement your own on top of that. Then we are having a graph storage layer. And the graph storage layer helps us to define graph-based data sets and graph-based data loaders. So in particular, we have support for homogeneous and heterogeneous graphs. You can have direct access to over 200 different benchmark data sets. And we also support 10 or dozens of different sampling techniques, which I will talk more about later. And then we have graph transformations and augmentations, which are kind of applied before we load in the data into our neural network architecture. And these augmentations are useful, such as like dropping nodes and edges during your training routines, which amounts to some kind of dropout. But you can also use that to transform your graph so that it fits into the needs of a GNN, such as defining meta paths on top and so on. And importantly, that scheme also, or this concept of transformation also allows us to not only support graphs, but also meshes and point clouds, in the sense that we can use k-nearest neighbor search on the point cloud to construct a graph on top of that, and then use PyG to process that graph. And we are working hard on making PyG the central place to practically learn about GNNs. So we now provide video, collabs, blog posts, and application-driven GraphML tutorials that let you practically learn about GNNs in the first place. And so I quickly want to show the general pipeline of how PyG looks in practice. And the main goal here is that we're trying to achieve is that PyG is like super modular. So in general, we want that each of these different steps can be easily swapped out. So you should be able to easily swap the GNN layer, see the performance. You should immediately see how the impacts of graph transformations and so on. So in the end, it always starts with the data you want to operate on. And as I said earlier, you have access to predefined data sets, but you can also create your own data sets on top. And then in your Python script, you just simply instantiate that graph and apply the necessary transformations. And so the graph creation step in PyG looks as follows. So we always expect a graph in either a COO or a CSR format, which are like the super popular sparse matrix formats. And that allows us to model complex heterogeneous graphs. So for example, we can instantiate a heterogeneous data object and then just write information to that object for different node types and edge types. So for example, we can write node features to a user and a product node type and write that to the attribute X. And then we can also write edge type information using this tuple annotation here, where we want to specify information from a user to a given product. And here we can define the edge index, which is basically the graph indices that describes this connection. We can add edge information, such as add features, or the time of these edges, and so on. Importantly, and what I want to highlight here is that in academic graphs, these data sets are already curated and ready to be used for us. But if you want to apply your GNN on your own industry graph, then that basically means you have to think about how you move your input graph to the expected format of PyG. And so what you need to respect is, for example, what is the best graph design that I can pick from that is suitable for this underlying message passing scheme of GNNs, in the sense that you want important information close by to target nodes. And then you have to think about how can I put continuous features into my neural network architecture. So we're speaking of feature selection, feature encoding, and so on at the level of graphs. After that, you're basically free to define any task on top of these data sets. And we usually use this Y notation here to specify like node labels and so on. And so, again, in academic graphs, these training labels and data splits are predefined and ready to be used. But in the industry setting, you have to, again, think about, like, how can I build my own training labels? And importantly, what are the data set splits I want to use? Especially, it has been shown that random splits are, like, overly optimistic, and better scenarios might be temporal splits and so on. Next, once you define your data set, you need to think about how you can obtain mini batches from that. And PyG provides over 10 different sampling techniques that work by subsampling subgraphs, and otherwise the graph would not fit into GPU memory. And so the general procedure here is that our graph is stored on CPU memory. We sample a subgraph, move that subgraph to the GPU, and apply a neural network on top. And afterwards, you are free to define your own custom GNN layer. And you have different flavors to choose from. You can use predefined GNN models that are used or that are built using state-of-the-art practices. You can build your own GNN layer with customized building blocks, as we are doing here, in the sense that we are using like a SageConf layer, which is a popular variant of a GNN layer, and then defining our computation graph on top. But you can also go one step further and just define your own GNN layers and use that in your custom GNN pipeline. And afterwards, the training and inference routines are like super straightforward and similar to vanilla PyTorch, in the sense that you just iterate over the data, you move it to the GPU, you apply the forward pass, you create the law or compute the loss on top of that, and then use backpropagation and gradients as descent to move the model parameters to the right direction. And so PyG is not limited by any of that. So you can have full customization from model architecture to training routines. But I think it's important to note that there are some concepts where you need deeper knowledge about GNNs. And in particular, it's important to note that the best model architecture is usually both data and task dependent. So what is the best GNN for the given task? How can we capture long-range information? You might find scenarios where you need to deal with class imbalances, overfitting, and so on. And that is hard to answer. It needs to be studied on a case-by-case basis. So that is the general overview of pipeline of PyG. And I quickly want to go a bit deeper on heterogeneous GNNs before I hand it off to Ramona. And heterogeneous GNNs are known as graphs where we have different node types and edge types. And that is here a classic example of a heterogeneous graph where we have like paper nodes, and these paper nodes are connected by which paper has cited which paper. And then we have author nodes, which are described by which author has written which paper. And then these different authors may also be affiliated with some kind of institution here. And then you can think about tasks such as what is the subject area of a given paper. So the general message passing scheme of a heterogeneous GNN looks super similar to what I've presented before, but it has some small differences. In particular, we are now only iterating over the neighborhoods that are bound to a specific edge type. So we first iterate over the number of relations in our graph, then apply a distinct GNN on top of that for each edge type we have in our graph, and then aggregate all these different embeddings we get together to get a final representation of a node. And so the general computation from a homogeneous GNN to a heterogeneous GNN may then look as follows. So on the left, we have the classic computation flow of a homogeneous GNN, which applies like different GNN layers, applies a nonlinearity between them, and so on, and then finally reads out these node embeddings. But in a heterogeneous GNN, it would look like follows. So we may have two node types, here denoted as H1 and H2. And then we create distinct GNN layers for each edge type in our graph. And here in this setting, we would have 3 different edge types. And then the computation is defined by which edge types aggregate information from which source node to the destination node. And so, since this looks similar, but is still different, we found a way in PyG to automatically convert homogeneous GNNs to heterogeneous ones using the PyTorch torch.fx package. If you don't know about that, I heavily suggest you look into that because it's pretty cool and lets you do really crazy things. And so in the essence, what happens here is that we create a homogeneous graph attention network here, which is known as GAT. And that just computes, that is a 2-layer GNN, and that computes like 72 output features. And then we call this 2hetero function here, which takes in the model the node types and the edge types in our heterogeneous graph. And that gives you a heterogeneous GNN back that is built on similar principles as the graph attention network. And what that does under the hood is that it duplicates the GNN layers for each edge type so that we have distinct model parameters for each edge type. It then transformed the underlying computation graph such that messages are exchanged along different edge types, as shown earlier. And then we're using this concept of lazy initialization here, which is known as this -1 in the input channels. And that allows us to handle different input feature dimensionalities without specifying them beforehand. And with that, I'm happy to hand it over to Ramona.
Thanks. Do you have any questions before we go into the practical sessions? Do you think you need anything before that? This is the QR code for the Colab notebook for all of those who want to also play a little bit around with it, then just scan that and open it on your computer. Okay, I don't see any phones anymore, so I guess you all have copied it. Yes? It doesn't open? It doesn't work?
Which group are we in?
Can you share it over the... I think we're A5. I can already start talking about the task we are looking into while you're copying the link. So we're looking into the movie lens dataset, which is a dataset containing information about movies and users that have rated the movies. And we're going to predict the rating a user gives a specific movie. Is there still anyone who doesn't have the Colab notebook open? Okay. But you have the link, right? Yes. Okay. So first, the notebook works a bit faster if we use a GPU. So if you go to Edit and then go to Notebook Settings, then you will be able to choose whether to use a GPU or not. So you can change that, and then the notebook, the training will be faster. And then first, for installing PyTorch Geometric, we first need to know which Torch version we have. And like the first cell gives you the option to check for the version, and then we see that the notebook already has pre-installed PyTorch 2.0. And with this information, it's pretty slow. Might be. With this information, we can specify the PyTorch Geometric version we want to download. So there are two libraries. We have the PyGlib, which is the foundational library, and then we have PyG, which we both want to install in the notebook. And then additionally, we have like 3 other libraries which we need for the preprocessing and for the explainability, but they're not specific to PyG. I think the installation also takes a couple of seconds. So as I said, like the goal of this practical session is to learn how to load a set of CSV files, construct a heterogeneous graph data object from it, and then learn a model on top of it for in our case, a link regression task. So we want to know how a user would rate a movie that the user hasn't seen before. Here we saw kind of like how the graph should look like. So we have like movies and then users, and we have information about which user rated a movie. So this is kind of the graph we want to construct. And like the data set is publicly available. It's like a toy data set created from the GroupLens research group. And we can just like specify a URL and then download the data set. It will then pop up here, and we can read in. We're especially interested in two different tables, which is the rating tables and the movie tables, and we can load them from the CSV file into a pandas data frame. We will see that each movie is assigned to different kind of genres, and we also have the title information and the release year of each movie. Additionally to the movies data frame, we also have a ratings data frame, which gives us information about the links between users and movies. So we see which user rated which movie with how many stars. So this is like the base data set, and I would kind of like to ask you to add manual ratings. So there are like two different ways how we can add our own ratings to that data set, because then in the end we also get personalized predictions. So if any of you have IMDb ratings, then it's very easy to export them and upload them. There's an instruction. It's like 30 seconds. Is there anyone who has IMDb ratings in an account? Okay, yeah, if you like, then you can do it. If for the others, there is, like, we have in total 10,000 movies. So the most rated movies are, for example, Forrest Gump or Jurassic Park. And you can specify how many movies you want to rate. So let's say we want to rate 4 movies. And then you can enter whatever movie you want to rate. Let's say Avatar. Then it gives you the whatever is in the movie data frame, which sounds similar as the title you entered. If it's one of the titles you want to rate, you can give the ID and your rating. And if you specify a couple of them, then you can in the end get a personal recommendation and then also see which of your ratings influenced the predictions. I'm also going to rate a couple of them. But yeah, you can also, I can also just upload my How's that work? Okay. I think that doesn't work at the moment, but yeah. Did anyone try to upload the IMDb ratings? Yeah? Almost, okay. In the end, you need to add your ratings to the ratings that were given in the data set. I'm still seeing some people adding movies and ratings. Okay. Anyone still wants to add more movies? More ratings? Okay, then I continue with the preprocessing. So we have now the pure table of ratings, including our own ratings. And then we also have the table of movies. We cannot put this as it is into a graph data object because we have, for example, the title, which is text and cannot be processed by a neural network. So we need to pre-process this a bit. So we first have the genre column, which we just one hot encode. So we receive a 20-dimensional vector. And then in addition, we also use a pre-trained sentence transformer model for the titles. This might take a couple of seconds. It will download the model and then transform the titles. We then concatenate the genre and the title features to one movie feature vector or matrix. We don't have in this dataset any information about users, so we don't know their gender or age or anything else. So we will just use an identity matrix for the neural network as input features. Then, those were the features for the nodes, but then we also want to somehow store in the data objects the connection between those nodes. And we do this with the rating CSV, where we have the links between them, and we will construct something called an edge indice, which contains the information of both which user linked what movie, and it will be in the form of 2 times the number of ratings. What we do first is, as in the table we don't have consecutive numbers, so we have, for example, movie 1, 10, and then 12, but there's no movie in between, and just to have it more compact, we map both the user IDs and the rating IDs to a consecutive range. So we create a data frame containing the original user ID and the mapped user ID, which is consecutive. Same for the movie. And after creating this, we use the mapped user ID and stack them together and receive a tensor which looks like this and contains all the edge or link information. So user 0, rated movie 0, and so on. We now are ready to construct the data object. So as Matthias already showed in his slides, this data object would look like we have a heterogeneous data object, and we would now pass the user features to the user attribute in the data object. Same with the movie features. And then we also add the edges to the object. Additionally, in this case, as the target is the rating, we add edge labels. So what Matthias showed was in the table was using an Y on a node, but in this case we're not predicting node type or node classification. We don't have a node classification task, and that's why we use an edge label. We also use one of the transformation function, which means we transform the directed graph. So at the moment we only have connections from users to movies, but we want also that the GNN is able to pass messages in the other direction, so that we can also learn something from movies to users. So we undirect the graph, which then also undirects the edge label, but we don't want to have the edge labels in the other direction, so we delete them again. And with this, we we create a heterodata object which looks like the following. So we have 9,000 movies, and we have 100,000 edges between them, and also labels on every edge, which represents the rating. And then we also have the reverse edges, but no labels for it. We are ready for training a model, but then before we need to split the edges into a training, validation, and test set. So we specify that we have 10% of the edges part of the validation set, 10% of the test set, and we split it randomly. Here we see that we have 8,000 edges being part of the train data. So the first data you see is the train data, and the second one is the val data. So you get back with this random link split function, you get back 2 new data objects. And what is also new here now is that we have the edge label index. And this one is required for telling the model on which edges we need to make predictions. So in the training data, we make prediction on all edges. But then, for example, in the test and validation data set, we have 10,000 edge label indices, but 8,000 edge labels, meaning we take the edge labels from the training set, use them as the basis, and then predict on 10,000 new edges that we add. Similar as Matthias described in the presentation, we can construct the model quite easily. We have here a specific way of constructing the model, as we have link prediction or link regression task. So we first learn an encoder, which learns an embedding for the user and for the movie. And then after passing the graph through the encoder, we apply a decoder, which combines the embedding of a user and a movie and then gives the rating based on the 2 embeddings. The GNN encoder is, I think, basically the same as the one we showed on the slides. So it's a homogeneous graph with 2 graph layers, graph convolutional layers. And then when we initialize the model, we can just transform it to a heterogeneous model. And the decoder is then, as I said, it combines. So you give in the edge label indices, which tells you which links you want to get a prediction for. And then you combine the user embedding and the movie embedding and apply normal linear layers on top of it to get a final rating prediction. Mm-hmm.
This 2 hetero function really sounds like a lot of magic is happening in there. So how long does this already exist? So is this, let's say, standard to use, or because I have the feeling that a lot of what is happening here depends on this particular function.
So 2 hetero exists for now over 1.5 years. It's pretty stable, but there are some corner cases where it might fail if you use like a super specific GNN architecture. But importantly, you don't have to use that. So you can easily convert like a GNN layer to a heteroGNN layer, and then build your pipeline in a more like fine-grained way, I would say. But I felt this 2 hetero conversion makes it like super straightforward to build like most of the classic GNNs, and just a useful helper function.
So here we see how the model then looked. So we have, as Matthias also said, we have a different convolutional layer for each edge type. And then in the end, we have the linear layers, which predicts the rating based on the combined embeddings of the user and the movie. And the training of the GNN is like very similar to any other PyTorch model. We first put both the model and the data on the desired device, and we initialize an optimizer where we specify some learning rate, and then we have like a training loop which just applies the data to the model. And then so here we see the one training loop. So we pass to the model 1x dict, which is like just all the features for every node type as a dictionary, and then we have the same for the edge indices. So this way you can access what we specified earlier in a dictionary. So here we specified it as an attribute of the data user, and here we get it as a dictionary. And then additionally, we also pass the labels we want to get ratings for. Then we get predictions out of the model, and we combine that or compare it to our actual ratings and compute the loss from it, and then update the model parameters based on that loss. That should go pretty quickly. So we see that we have like a training error of 0.8 and a validation error of 0.89 or 0.85 for training, which kind of means that like the prediction of the rating is 0.9 off from the actual rating. This is kind of due to that the data set is very small, and we also haven't like fine-tuned the model a lot. So that's a very basic model. And we can just apply the same to the test data, and kind of see here visualized for which user, which movie, what we predicted as a rating and what the actual target was.
Why do you need the two CPU function here for that method?
Here?
Yes, in the user, yeah.
It's just because otherwise the data frame doesn't, it's just for visualization. So now coming back to our own ratings we gave, as we have now trained the model, we can just, like this cell implements that you get a random movie, which for example here is for me the reader, and then you can, in the next cell, get how many stars you would give to this movie, even if you haven't seen it. So it will just generate a random movie that you haven't seen, and in the next cell, we will see that the model thinks that I would give 4.3 stars to this movie. Yeah, I should probably watch that. Final, last step. Since a couple of months, PyG also supports explanations, or we had like GNN explainers before, but now we have a general framework for explainers. So we can also look into what influenced the predictions and use different kind of algorithms. Now I kind of like want to know why and what influenced the decision that I would like the movie The Reader and would rate it that high. And what I can do in PyG then is use the explainer class. I would like pass that explainer class my model. And then also I would select the algorithm. Captum is also just like an open source library for explainability or interpretability. And we build a wrapper around Captum such that Captum can also be used with GNNs. And Captum has a list of different attribution methods, including integrated gradients. So we can just specify that here and use that integrated gradient attribution method from Captum. We also specify that we want to get an explanation for the model output. What you can also do in case of a classification, you can, even if the model output is that it would predict class 3, you can still ask for an explanation why it didn't predict class 1. And then you would give here not the model, but the class you want to predict, if you want to get the explanation for. We also specify some information about our model, such that it's a regression model. The task level is the edge, and the return type of the model is the raw output. There are different kind of explanation we can get. We can get information on, for example, node features. So how important was the title of the movie for the prediction? How important was the title of the movie that is like 2 hops away, that someone else as a user has rated? And we can get information on the importances of edges. And here I'm only going to look into the edges. And we can just call the explainer with the data we have and the edge label. And the edge label here in this case only contains the indice from my user and the movie, the reader. So you get like one explanation for this specific link prediction case. It outputs heater explanation object, which contains again the user and the movie information and also the original edge index information. But then additionally, we also have something called edge mask, which contains the information of how much each of the edge contributed to the final prediction. As there are many edges, like 90,000, we don't want to look into all of them. So what the next cell does is first, what do we do here? So we output, we just concatenate both edge masks to one data frame, and we see kind of that the user 231 rated the movie 3,445, and then we see the attribution of this link. So it's in this case negative, and means that the case that this user rated this movie kind of like shifted away the prediction, meaning that if there wouldn't be this link, then the prediction would be higher. So then we would, for example, get 4.2 or 4.3 as a prediction instead of 4.1. To make it a bit more clear, we only look into the movies we rated. So I want to know how much did the 2 movies I rated the Schindler's List and Avatar, how much did they contribute to the final predictions? And we see that the fact that I rated Schindler's List contributed more than the fact that I rated the Avatar movie. That's it. That was the practical part. I can take now some questions if you have questions on the notebook. Otherwise, we have a couple of slides left, and then we can go later for the Q&A session.
Yeah, there is one question online. Maybe I should read it. What is the estimation function? It can be a neural network.
Maybe the person can clarify the question.
Well, it might be also from the internet.
Maybe a different question.
Mm-hmm.
Do you have another example for graphs? Or, I mean, it was very interesting, but still quite a difficult concept. So, what else we could imagine as a graph, or with different sizes, with the edges?
I mean, kind of like a typical business graph could be that you just have users and products, and that would be already a heterogeneous graph if you have information about whether a user bought a specific product. That is, I would say, kind of a typical business application.
Can you give an example for traffic subway?
Do you have one? I mean,
So a traffic network would look like where you have a crossroads as nodes, for example, and then like these edges would denote like roads, and then you would have edge features where how long it usually takes to travel a certain road and so on.
Okay.
And then you can use that, for example, for navigation and so on, and that is actually what DeepMind is doing as well. As far as I remember, there was some highlight last year or something like that where DeepMind like revolutionizes traffic prediction using GNNs. Yes?
A more general question. So is PyG actively supporting alternative accelerators like GraphCore IPUs? Do you know that?
Oh, that's funny because we just came back from a London event where we announced our collaboration with GraphCore IPUs. And GraphCore published a bunch of notebooks on their end, and they have some Paperspace notebook experience where you get like 6 hours a day for free to use GraphCore IPUs with PyG.
Okay, great.
want to continue?
Okay, so I'll quickly wrap this session up. And so what you have seen here is how the different problems of GNNs, how they are defined, and how you can practically use them. And I see personally PyG as a low-level library, like an engine where you can like fully customize everything. But that usually also comes with certain disadvantages. So, for example, I often get complaints about that one needs GNN expertise to use that. For example, you're still responsible for feature engineering parts and coding parts, how you actually define your graph and so on. And so if you're not fully into GNNs, it might be a steep learning curve. And we're trying to bridge that gap by providing many, many tutorials and so on. But in the end, if you really want to productionize it as well, there's an additional layer of complexity that comes into play. For example, currently PyG only supports like CPU-based graph storages, and you would have to think about how you can connect to a graph database and so on. And if you want to write like daily batch predictions and so on, you may want to manage the life cycle of your graph so that you update your graph regularly on a scheduled basis. And then there are some additional questions like production orchestration and so on. And so what we're also trying to do is that we're trying to build a framework on top of PyG, which we named Kumo, that automatically tries to overcome all these problems at once. And so the goal here of this new framework is that you don't need to really dig deep into GNNs and just use them if you want to. And so what that looks like in practice would be that you can connect your raw data using one click. And so you could connect to S3, data warehouses, and so on. And that builds on the premise that all your data is kind of stored in a relational database. And so what Kumo then does is that you connect your tables into the Kumo framework, and then you specify how these different tables are connected, for example, using primary keys, foreign keys, and so on. And then we're building this graph from scratch for you in the sense that we connect foreign keys, primary keys, so that gives us direct linkage. But we're also doing some more advanced options here, such as bringing tables that are far away in the graph nearer to the table you want to make a prediction for. And then we think about how we can make formalizing the task as easy as possible. And we're coming up with a declarative language here, which we call predictive query, where you can just say for which entity you want to make a prediction for which time frame, and based on what target. And in that case here, for example, this simple query language would look like that we are interested in the average amount of the balance between now and the next 90 days for each user account. And that's a framework we're currently building that uses PyG as the engine, but gives you like a more high-level interface to get familiar with GNNs. And with that, I'm happy to conclude this session here, and we're both happy to answer any questions if there are any. Yes?
So you mentioned that it's difficult to deploy these GNN networks.
Yes.
But could you give like a couple of examples, but like compared to deploying like a deep neural network? Like what would be like an additional maybe challenge or something?
So I would say the two most problematic challenges is scalability and updating your graph. So usually if we think about large-scale graphs, we speak about 15 billions of edges, for example, and then you can no longer store that in a CPU. You need like a distributed learning scenario and so on. So that is one challenge. And then the other challenge is to constantly update this graph over time, because graphs are usually changing, and you always, if you want to make a prediction, you always want to incorporate the latest information into your GNN. And I would say these are the two biggest problems here to overcome. Yes?
I'm not sure. Okay. Yeah, one question I have, like, when you have like certain business rules, how can you also model that somehow on the graph? Like when you know like a link should never exist or should always exist, so it's like you kind of don't want to learn that part, but you still want to be somehow able to feed in the graph completely? Or do you have to do this like more like afterwards, like that you have like the post-processing step or maybe a preparing step?
Oh, okay. You want to take that, or okay? I'm not fully sure I understood that question, but I may be able to give you an example. So there's one line of research which is called like signed graph neural networks, where you can specify like, is it a positive edge, is that a negative edge, and then you could specify these rules as part of your input graph, and then the GNN should be able to learn and generalize that rule across the prediction. Does that answer your question to some extent?
Yeah, maybe I could make it a bit more specific, but if it goes like into this like usual use case where you like have user and products, and you just know that certain product combinations are not possible. Like if user has like product X and Y,
Yes.
then you just know that you cannot have like product Z, and that you can somehow like give this information.
Okay. So there are two adjustments here you would need to make. So if you train that model, that would be you're responsible for defining the negative sampling strategy. And if you're sure that like you never sample a certain set of nodes, then there's no point to include that in your negative samples. And then in the batch prediction phase, where you really want to predict GNNs, you wouldn't need to predict on the set of nodes that are like not included in the set that you want to make a prediction for. Like if you want to, for example, recommend a store for a given user, then it makes no point in recommending a store that is like in the USA right now. And so you would never just input that into the GNN. So technically, if you train it that way, it would give you probably a low score for these stores as well. but you would still need to compute that, right? So if you know about that in advance, you should include that in your preprocessing pipeline. You're still not looking super happy, but
Yeah, maybe. Yeah, because but I think I kind of understood your answer, but I still need to think about it more. But I think
okay, happy to follow up with that. Yeah, the man in the green shirt.
So yeah, first of all, thank you for the great workshop and also for this amazing library. And I'm very happy to see that you're also making it like a place to learn about GNN, so that's super cool. And my question is more of a philosophical question. You have been talking about a lot how, we know that graphs always change. That's kind of a fact. But there are also specific libraries that I think also build on top of this that include like this temporal dimension explicitly. So my question would be, like, what's your perspective on including this type of information explicitly into a graph or not? And I mean, it would make sense to also include something like that into PyG.
Yes, so that's a very good question. So there exist indeed like extension libraries built on top of PyG, and one of them is known as Phytogeometric Temporal. Sadly, I think it got really successful, but it doesn't look really maintained right now. So we're trying to move some of this to PyG native directly. And I don't want to spoil too much, and I'm not even sure if I'm allowed to talk about that. But I think we're on the internet as well. But anyway. So what we're building in combination with PyG is like a temporal open graph data set that really drives or tries to drive the efforts of building more temporal GNNs from the community. And in combination with that, we're fully trying to support more temporal graph GNN models into PyG as well. And that is, it's not ready yet, but we're thinking about that, and we're making great progress for that. But just to finalize, there exists already some GNN models in PyG that can make use of temporal GNNs, and we also support like advanced data processing such as temporal sampling and so on. So that is all ready to use. But I wouldn't say it's like 100% done. Probably it's never done, but we're working towards that. Yes?
Thanks for giving this workshop. And PyG definitely looks very cool as one big library that does all the things you need to do with graphs. I have a question regarding the computational backend. So right now it looks to be built around PyTorch. How easy would it be to swap the computational backend for something else? To be able to say, okay, I have a tensor for my parameters for the edges, and I don't want it to be a PyTorch model in the end, but a model built with, let's say, TensorFlow or PyTensor or JAX or whatever. How hard would it be to
Critical question. Okay. First of all, we have been moving away from our own external libraries, and so we're mostly fully relying now on native PyTorch, which helps us tremendously in the way we can export PyG models. So we can use like ONNX, we can use TorchScript to export our models, and that is all fully supported. From the perspective of supporting different deep learning libraries, I would say PyTorch is so coupled with PyG that it's like super hard to move away from there. And so we're really relying on the success of PyTorch here, I know. The one thing I would say is that it gives us many advantages to just rely on a single deep learning library, because we can use like new features introduced that directly into PyG. And so we're also working closely with the PyTorch team, and as a result of that, like they heavily improved their sparse matrix support and so on. And that is something we cannot really get if we're relying on multiple backends. So then we are just limited by the union of features of all these different libraries. And I think that's like an important consideration to make. I probably wouldn't change that direction if I would start from scratch. And so, yeah, we're relying on exporting models if you want to use like TensorFlow or so on. Yes? Okay, very, very good question. So we had a workshop last September where we announced like PyG 2.2, and that release comes with a clear interface to connect to different graph backends. And so what we do is we provide interfaces for a feature store and a graph store, and that basically allows us for independent scale-out, independent of CPU memory. And so if you implement that interface of graph store and feature store, for example, for Neo4j, then that would mean that we can directly sample subgraphs and sample features from that graph database, and that would produce us PyG mini batches. And so what we do right now is we're working with several graph database providers such as TigerGraph or Kuzoo, and they have been both able to implement that interface. And I'm not sure, previously I talked to someone from Neo4j, but we have that on the roadmap as well. Yes?
Thank you so much. I do have a question regarding the scalability. So you already mentioned the whole setup is broadly vastly scalable due to the usage of bare bones storage backend. Is it like thinkable of using the graph neural network setup with all the cross-task kind of tasks, let's put it like that, being multi-target prediction or having your node metadata, node description being pictures or any sort of other different non-tabular inputs to combine those approaches, say, in order to predict not only the ratio or the what was that, the IMDb score, but let's also predict a second dimension of target, the amount of popcorn needed, for instance, or also like putting a teaser into an input, like a short frame. Is it already something that one could possibly, or is it in development?
So that is like fully supported. Mm-hmm. It just needs to be written by you. And so what that means is like you have full control, full customizability of the training loop. Like if you want to predict like a multi-target, then you just output 2 predictions instead of 1 and train that together, right? So that is super, super straightforward. Regarding your question about input features, that is a tricky one because you always need to encode your features, right? Mm-hmm. And you can either then, like if you want to include like image covers of all the movies, for example, you can either like use a pre-trained ResNet, compute the embedding, detach the embedding from the computation graph and just use them as input features, or you could jointly train your CNN and GNN together.
You can just stack them.
The problem with that is that this likely yields you a GPU memory error. Because what we see, for example, in this demo is that we are operating on like 1K or 10K movies for a single prediction. And that would also mean that your batch size in your CNN would be around the same, right?
Yeah, but theoretically, I mean, of course,
With unlimited GPU.
Practically, I wouldn't do that. I would split the task, but theoretically.
Yes, with unlimited GPU, all of that supported.
Cool, thank you.
Yes.
Yeah, I have a kind of question. So I tried PyG before, and one thing that got me confused is, so I tried to split the data differently. For example, if I do 3 experiments, and each time I split data differently. Then I look at the graph representation. Every time is completely different. So I'm wondering if this is because, or maybe it's because my problem doesn't require graph, or is just something natural is happening. So I'm just wondering, like, in practice, how can I interpret this?
Okay, not fully sure I can help you with that, just on a high-level thought, but so the problem is that if you have a graph data set and you split that, your graph data set looks different afterwards.
Yes.
Every time you run the split.
Yes.
And that is with a fixed seed, so the number...
Yes. But each time it gets different data, different training data, because I do different runs.
And that is a node-level task or a graph-level task?
It's a graph level.
Okay, but that should be the case. So maybe, I don't know, maybe the seed isn't respected by some random operator or something like that. Otherwise, I'm not sure. Happy to help you out on Slack or GitHub with that problem. I think it's solvable. Yes.
I have also a question, but maybe more regarding Cuma, because more from a, prompt engineer perspective. Like, we had an example about these movies, and we had individual inputs from everyone, and we had individual results. But let's say we want to have a movie night, and people rate movies differently, but we don't want to end up with a trailer night, so we just want to decide which movie to watch, like a collective decision. Can we make this with the framework as well?
Interesting question. So like the first thought that comes to my mind is that you're just predicting the top K movies for each user and then try to learn like how to combine them, right? But if you think about something more fancy, I would say you can add these clusterings as part of your training pipeline. So in the sense that you have some kind of hierarchical graph. So like a user rates a given movie, and then you have like a cluster of users that rate a given movie as part of a group or something like that. That would be something that would be doable, but I'm not sure if it's really practical to do that.
Sounds like hyper-edge.
Yes, so that would be related to like a hyper-edge GNN, yes.
So it's not just averaging, it's already...
So the way you would treat that is that you somehow learn how to aggregate the information from each user into some kind of cluster decision, exactly. And ideally, you want to train that as well. Might work, might not.
But Cuma can do it?
That's something we haven't looked into it, to be honest. If you define the clusters as part of your graph, then we can do it. Yes.
Thank you very much for your very interesting...
Thanks for attending.
mastermind.